Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today, we have set our hearts to solve a paper 2, which we call theory paper, and we have selected October November 2022 2 paper. This paper 2 belongs from the Zone 2, or you can say the Variant 2. In this video, I'm going to represent you the solution of the section B of this paper. The section A of this paper I have already solved, and it has been uploaded in my YouTube channel, and in the same playlist where this video is, you can find the section A of this paper. So let's start the section B of this paper. So the section B starts from the question number 7. He says copper is sometimes chosen as a material to make pans for heating liquids. A copper pan contains water at room temperature. The top surface of the water in the pan cools as water evaporates. A convection current causes the rest of the water to cool. Explain how this convection current is produced. You see, from the top surface, the evaporation is happening. So the top layer becomes colder, and when the water becomes colder, the molecules they come close to each other, and on the top, the cold water will become dense, and the water at the bottom that will be relatively hotter. Its temperature will be more as compared to the top water. So that dense water, because it's dense, and the water at the bottom, which is hotter, it will be less dense. So this less dense water rises upward, and the dense water sinks downward. So this creates convection currents in the water, and this way the water, the convection currents are produced in the body of the water when the top surface becomes colder. So this is my description. So here is the written answer, which I think can be the answer, and I always hope that you can write a better answer. This is just an idea how the answer should be written. Cold water on top of surface is denser than the water in the body of the liquid. Molecules of the water are closer on top of surface. On the top surface, dense cold water sinks and hot, less dense water rises upward. This sets in convection currents in the water. That's question number 7A part. The marking scheme of the question number 7A part is showing up on your screen. You can pause the video and you can take more time if you want more time with this marking scheme. This is the solution, A part. Question number 7, B part. The copper pan is now placed on a hot plate that is switched on. Name the process by which the thermal energy passes through the base of the pan. The base of the pan is solid, and through the solids, and it's made of metal. The thermal energy transfers with the help of the conduction. So the answer is conduction. Question number 7, B part, conduction. Okay. Now the second part, question number 7B, second part, copper remains a solid when heated up to 1,000 degrees centigrade. State one other reason why it is sensible to make a pan out of copper. You see, copper is a metal and it has free electrons, so it is a very good conductor of the heat as compared to other solids. Copper is a metal. It is a very good conductor of heat. Conduction is a good conductor. Yeah, our answers are right. This is the answer. Here we go. Question number 7, it's C part. He says the water in the pan is heated 17 degrees centigrade until it starts to boil at 100 degrees centigrade. The specific heat capacity of water is 4200 joules per kg per degree centigrade, and the pan contains 750 grams of water. Calculate the energy needed to increase the temperature of the water from 17 to 100. So you know the heat is equals to mc delta theta. So the heat which you need, because here the temperature is changing, the formula is m C and delta and theta, where this is the mass and this is the specific heat capacity. And if you look at here, in the unit of the specific heat capacity, the unit of the mass is kg. So the mass here should also be in kg. This is the trick here. The unit is joule per kg per this, and this is the change in the temperature. That is 100 minus 17. It will be the change in the temperature. So very simple. This is how you do this. Let me show you. I have done this. Okay. So heat is equals to mc delta theta. The mass must be in the kg because the unit for the mass in the specific heat capacity is kg. So 750 grams divided by 1000 multiply 4200 multiply. So 17 minus 100 minus 17, and when you do this on your calculator, you get 261450. When you write it in the standard form, it is 2.6 x per 5 joules. 2.6 x per 5 joule is the answer. This is the marking scheme, and this is the solution. Okay, then their question is, state two ways in which boiling differs from evaporation. You see, when the boiling happens on a specific temperature, when the boiling is happening, the temperature will not change. And the evaporation happens on all the temperatures. And when evaporation happens, the temperature changes. In the boiling happens throughout the body of the liquid. Evaporation happens only on the surface of the liquid. When the boiling happens, the air bubbles are formed in the body of the liquid. And when the air bubbles, and the bubble also has steam, and during the evaporation, no bubbles are formed. So these are the few. Okay. Boiling takes place on a specific temperature. Evaporation takes place on any temperature. On all the kind of temperature it takes. Boiling takes place in whole body of liquid. Evaporation occurs on surface of the liquid. So here we have, this is the answers, and you can pause the video. You can take your time with this marking scheme. So this is my answer. Okay, so question number 7, and it's C part. It's fourth question. He says the specific latent heat of vaporization of water is 2.3 expo 6 joules per kg. The thermal energy is transferred to the boiling water at a rate of 1300 joules per second. Calculate the mass of water that boils away in the 10 minutes immediately after the water reaches 100 degrees centigrade. Okay. I think we have missed. Oh, sorry, I missed one part, this third one. Okay, so let's do the third one first. Sorry, I missed the third one. At 100 degrees centigrade, the temperature of the water stops increasing, even though energy is still being transferred to the water. Explain in terms of molecules why thermal energy is needed to change the state of water from liquid to gas. Okay, so at boiling point, the heat is being provided, but the temperature do not rise because the heat is used to move the molecules of the water away from each other. The heat is used to break the intermolecular bonds. The heat is used to yeah. So heat is used to overcome the atmospheric pressure. So heat is not used to increase the kinetic energy. Okay. Energy is used at the boiling point. The energy is used to increase the distance between the molecules of the water. Energy is used to break intermolecular bonds and overcome intermolecular forces. Energy is used to overcome atmospheric pressure. Energy is used to increase the potential energy of the water molecules. So that's why no temperature rises. Okay, so he says, does work against the forces, break the bond between the molecule, increase the potential energy of the molecule so that as the molecules move apart, separate and become gas molecules. Okay, so we are going to next part. That is the fourth part. He says the specific latent heat of evaporation of water is 2.3x per 6 joules per kg. Thermal energy is transferred to the boiling water at a rate of 1300 joules per second. Calculate the mass of the water that boils away in 10 minutes immediately after the water reaches. So we know the time, we know the rate of the transfer of the heat. Just multiply these two, but this should be converted into seconds. And then you will know how much heat is provided. And then I can use the formula for the heat is equals to ml, where m will be the mass, l will be the specific latent heat. And we can calculate how much mass of the water will be converted into the steam. And so energy is equal to power multiplied time. So power is 1300 and the time is 10 minutes, which will be 10 multiplied 60. So that will be 780,000 joules. So the heat is equals to ml. So m will be equals to q divided by l. So m will be equals to 780,000 divided by 2.3x per 6. And mass will be 0.339 kg. And when you round it off, it will be 0.34 kg. 0.34 kg is our answer. 0.34 kg is the right answer. This much amount of water will be converted into steam. Okay, so my dear students, now we are on the question number 8. He says an uncharged plastic rod is rubbed with an uncharged woolen cloth. As a result, the rod becomes negatively charged. Explain in terms of particles how the rod becomes charged and state what happens to the cloth. You see, when you rub them together, the rod becomes negative. That shows that the electrons from the cloth has been transferred to the rod. That's why the rod is negative. And because the cloth, it has given its electron, so now the cloth will become positively charged. So during rubbing, electrons are transferred from the woolen cloth to the plastic rod. Rod becomes negatively charged, woolen cloth becomes positively charged. Question number 8. You can see the marking scheme. This is my solution. Okay. Question number 2, he says figure 8.1 shows a metal sphere X on a plastic stand. So this is a metal sphere X. This is the plastic stand. Explain why metals are electric conductors and why plastics are electric insulators. 2 marks question. You see the metals have free electrons in them which can flow in the body of that metal. And so those electrons helps in the flow of the electricity, flow of the charges. And the plastic, it does not have free electron. That's why it's an insulator. And metals are a conductor. Metals have free electrons which can flow in the metal. They help to flow electricity in metal. Plastics don't have free electrons, so electricity cannot flow through plastics. So that is my answer. Question number 8, B part. You can see the answers are here. You can check the marking scheme. Okay. So we are going to the next question. That is question number 8. It's C part. He says a negatively charged plastic rod. A negatively charged plastic rod is held above the sphere X. Figure 8.2 shows that it does not touch the sphere. By drawing on the figure 8.2, show the distribution of charges on X. So see, due to this, the electrons will be repelled here. So the top will become positive. So this portion will become positive. And here the electrons will be accumulated. So electrons will show up here. This is a 2 marks question. I have also done this. You can see this diagram. I have also done here, and look at the marking scheme. Okay. Then he says an earth wire is now connected to the metal sphere as shown in the figure. State what happens to the charges on the sphere as the earth wire is connected. When you will connect the earth wire here, these electrons through the earth wire, they will go into the ground. So this is what will happen. Negative charges electrons through the earth wire goes to ground. Top of the sphere remains positive, but those electrons will go into the ground through the earth wire. Only this is the answer, G. Negative charge electrons flow to the earth and the positive charges do not move. Okay. Then their question is, the earth wire in second part stays connected to the metasphere. Describe the distribution of charge on the sphere. You see, if this earth wire remains here and this rod also remains here, so what will happen? This top will be positive, but this portion will be neutral. Top of the sphere remains positive, bottom of the sphere becomes neutral. That's my answer. The answer is right. Okay, then they say fourth part. The earth wire is disconnected from the sphere and then negatively charged rod is moved away from the sphere. Explain what happens to the charge on the sphere. So now what they will do, they are going to break this earth wire first, and then they will remove this negative rod also. So what will happen? The whole of this rod will become positive because it has already lost electrons to the ground. Charges repel, the positive charges which were on the top, they will repel each other and they will be distributed on whole of that sphere. So charge repel, the positive charges repel each other and are distributed all around the sphere, and the sphere becomes positively charged. That's question number 8C. This is the answer, fourth part. Okay, then we have the D part. He says, second metal sphere Y is negatively charged. There is an electric field surrounding Y. State what is meant by electric field. Electric field is basically a region around a charge in which another charge will experience a force of electrostatic force of attraction or electrostatic force of repulsion. So that region around that charge is known as the electric field. Region around a charged body in which other charges experience electrostatic force of attraction or force of repulsion. Yeah. Then he says, figure 8.4 shows negatively charged sphere Y. The negative charges are not shown. Okay. On the figure 8.4, draw the pattern and mark the direction of the electric, because this is a negatively charged. So the electric field lines, they will be going towards it. This. Okay. So my dear students, now we are on the question number 9. He says protactinium 234 and is a radioactive isotope of the protactinium that decays to uranium 234. Compare the nuclide notation of protactinium 91-234 with the nuclide notation of the uranium 92-234 and deduce what this shows about what is emitted from the nucleus of the protactinium 234 as it decays to uranium 234. Place a tick in the appropriate box. If you look at them here, look at here. So you can see the proton number has increased by 1. The proton number has been increased by 1. And the nucleon number, or which we call the mass number, that has not changed. And how this is possible? This is only possible when a beta particle is given out. Whenever a beta particle in a radioactive decay, beta particles are given out, the daughter nucleus, its proton number is one more as compared to the parent nucleus, and its nucleon number do not change, its mass number do not change. So clearly this shows a beta particle has been uh, given out. Please place a tick in appropriate boxes. Table 9 show what is deduced from comparing the nuclide. An alpha particle is emitted? No. A beta particle is given out, emitted? Yes. A gamma rays is given out? We cannot say. Why we cannot say? Because when the gamma rays are given out, the proton number do not change, the mass number do not change. So for gamma, we are not sure, but okay. See, this one is very tricky, especially about the gamma. Okay, so the B part of the question number 9, he says the most abundant isotope of protactinium is protactinium 231, explained by referring to their nuclear composition. Why the protactinium 231 and the protactinium 234 are both isotopes of the same element? You see, they both of them have the same proton number, but their nucleon numbers are different. The number of neutrons in their nucleus, they are different. That's why they are the isotopes of each other. He says the both protactinium 231 and protactinium 234 have the same proton number 91, but their nucleon numbers are different because they have different number of neutrons in their nucleus. So that's the question number 9B, first part. Okay. Then their question is, explain by referring to their nuclear composition why protactinium are different isotopes of that element. And because they have the same proton numbers and their nucleon numbers are different, that's why we can call them, their isotopes. Protactinium 231 has 91 protons and 140 neutrons, and protactinium 234 has 91 protons and 143 neutrons in their nucleus. That's why they are the isotopes of each other. Okay, so that's the marking scheme. The first part, you are only supposed to tell that their proton numbers are same. Question number C, first part. The teacher places a radiation detector on a bench in a school laboratory and switches it on. The teacher measures and records the background radiation count rate. Describe what is meant by background radiation and state two significant sources of the count rate recorded by the teacher. Background radiation is the radiation which is always present in our environment in a location. So we say that is the background radiation. The sources are the rocks. It can be the rocks, and it can be the cosmic rays which are coming from the outer space. Radiation which is always present in the environment is called the background radiation, and the sources can be cosmic rays from the sun or the radioactive minerals in the rocks in that area. So these can be there are many other reasons, and some of them are listed here. Count that is present or due to the environment surrounding or not deliberately introduced or not being tested. Any two-formed rock source, for example, benches, building materials, human body, earth crust, air sources, for example, radon, and cosmic sources, for example, sun and space. Okay, then they say the teacher moves a sample of protactinium-234 so that it is next to the detector. So just one precaution that ensures that the sample is moved in a safe way. You see, there can be many ways. For example, whoever is the working, he should be wearing an apron which has the lead lining. He should be wearing gloves with the lead lining. The exposure time must be kept minimum. And when you want to move them, you should use tongues to hold that sample, and other precautions are there. You should wear safety goggles. Radiation, use tongues to hold and move radioactive materials. So this is just one precaution. So here you can see a list of different things which you can use tweezer, you can use forceps, and wear lead lining also. This is the answers. The count rate is measured every 20 seconds with the sample present and then corrected for background radiation. Figure 9.2 shows a graph of corrected count rate. This is already been corrected against the time of the protactinium 235. So here, what will be the reading? I think it's it's 50, 58, 59, something. And okay, so the reading is 58. Just note it down. So after when the half-life pass, it will become half. So divided by 2, that's 29. So from the graph, I will check where is the 29. 29 will be, this will be 20. And this will be 30. So here somewhere, okay. So here somewhere it will be. So this is 2966. So that means it has taken 66 seconds to the count rate from 58, it dropped to 29 in 66 seconds. So half-life is 66 seconds. Half-life is the time duration in which the sample will become half. So it was 58, it becomes to 29, the count rate, I mean. Okay, so the curve is the best fit line. Explain how many of the crosses, explain why many of the crosses do not lie on the curve. You see, some are above, some are below, okay? The reason is because the radiation is not, it's a random process, okay? So because it's a random process, so every time you take the reading fluctuates, okay? So he says the radiation is a random process, reading on the detector will fluctuate. Okay, that was the previous part. Half-life we have determined already. Then he says the uranium-234 formed from the protactinium-234 is also radioactive. Its half-life is many thousands of years. We know that it's 5,700 years, approximately. I know from the other textbook that its half-life is this much. Explain why the radiation from uranium-234 does not affect the count rate measured in this experiment. You see, its half-life is 5,700 years. So its decay is very slow. So during these, how many seconds we have observed? We have observed only for 320 seconds. So in the 320 seconds, it will not give out any kind of radiation, hopefully, and it will not affect the reading because its half-life is 5,700 years. So its count rate is radiation process, is decay process very slow. Larger half-life because of slow rate of decay. acceptable, very less than. Okay. So my answer is yes. Half-life of uranium-234 is 5,700 years. Its rate of decay is very slow as compared to the protactinium-234 rate of decay, whose half-life is only 66 seconds. So in 320 seconds, uranium will not affect the reading of the detector. Okay. So the answer is already here. This is the answer. So my throat is sore. So okay, so my dear students, today we have completed the October-November 2022 2 paper. In this video, we have done the section B of this paper. The section A of this paper I have already done, and it has been uploaded in the YouTube channel. Both these sections will be in the same playlist. And if you think that this video has helped you, please share the link of this video with your junior students, senior students, with your parents, with your teachers, with other people who are doing the Cambridge O-level physics. That helps me also to promote my channel. I think it's a great blessing for me that I can make these videos which touch the life of so many students. And special thanks to Karachi, to Lahore, to Dhaka for watching my videos. Thank you very much, sir. Have a good day. God bless you all.